Mechanical department, and today I'll be talking about matrices and matrix multiplication. So what exactly is a matrix? Let's talk about the simple term. It's nothing but a rectangular array of numbers, symbols or expressions arranged in a organized row or column. And so let's talk about a more mathematical definition of a matrix. Suppose we say that a matrix exists of an order of m into n, which means that the matrix has m rows and n columns, where m and n can take any integer value. And let's go more into the world of matrices. There are several types of matrices. For example, row matrix, column matrix, square matrix, diagonal matrix, and zero matrix. So what is a zero matrix? A matrix which has all the elements in which all its elements are zero is said to be a zero matrix. And what is a square matrix? A square matrix is a matrix where the number of rows is equal to the number of columns. So this concludes the different types of matrices. Basic arithmetic operations like addition, subtraction and multiplication can be performed upon matrices. And now we'll be talking more about the arithmetic process multiplication on matrices. Suppose I take two matrices A and B. They can be multiplied only if the number of columns in matrix A is equal to the number of rows of matrix B. I'll repeat it again. Two matrices A and B can be multiplied only if the number of columns of matrix A is equal to the number of rows of matrix B. This is the basic rule of matrix multiplication. And also a matrix, suppose a matrix A has an order m into n and a matrix B has an order n into p. Then the product of matrix B into A is not defined, it will not be defined if P is not equal to M, where P represents the number of columns of matrix B and M represents the number of rows in matrix A. This also implies that AB is not equal to BA. That is, the product of matrix A into matrix B is not equal to the product, is not always equal, I would like to emphasize on that, to the product of matrix B into matrix A, which says that matrix multiplication is not commutative. But however, in some cases, matrix multiplication can be commutative. Let's talk about the various properties that matrix multiplication possesses. So the first property we'll be discussing about is associativity. For what exactly is associativity of matrix multiplication? It says that suppose we take three matrices A, B and C, then AB into C is equal to A into BC, provided the products A, B and product BC are defined. The second property we'll be talking about is distributivity over addition. For example, we take three matrices A, B and C, then A into B plus C, which means B plus C represents the sum of matrix B and C, is equal to AB plus AC, and A plus B into C is equal to AC plus BC. That is, I'll repeat again, A into B plus C is equal to AB plus AC, and A plus B into C is equal to AC plus BC, provided once again the products AB and BC and CA are defined. And the third property we'll be discussing is the existence of an identity. We all know what exactly is an identity is. So let me elaborate about it more here. For example, I take a square matrix A. There exists an identity matrix for the same order, in the same order. That is, I into A is equal to IA, where I represents the identity matrix, and I into A is equal to AI is equal to A. That is, a matrix, suppose a matrix A is multiplied with the identity matrix, it yields the same matrix again. That is why the matrix is called the identity element or the identity matrix. More on the process of matrix multiplication, and hence I'll show you the working of matrix multiplication on paper. Suppose I take a 2 into 2 square matrix of order m into n. Suppose with random elements. Here I take random elements as 2, 1, 3, 4, and this is a matrix of order 2 into 2. And let me try to multiply it with a matrix of order 2 into 1. That is, it has 2 rows and 1 column with once again random elements. Suppose I take 5 and 6. So the first element is a matrix of order 2 into 2, and hence I write it as m into n, where m is equal to n. And the second matrix as a matrix of order n into p. And here let's check the condition for matrix multiplication, which we had discussed before. Here the number of columns in matrix 1 is equal to the number of rows in matrix 2. Hence the condition is satisfied, and hence we can multiply these matrices. And the product yielded by the multiplication of these matrices will have an order of m into p. That is, the product will possess an order, will have an order n into p. Now let's proceed with the process of multiplication. Here this is how the process of multiplication works. You multiply the first row, the row in the first row in the matrix 1 with the column in matrix 2. That is, so you multiply 2 and 5. So 2 into 5, and you sum it up with the product of 1 into 6. That is, the other element in row 1 with the other element in from the column of matrix 2. That is plus 1 into 6. And for the second row, you have to multiply with the column again. So it will be 3 into 5 plus 4 into 6, and sum it up with the second element in the second row with the column, with the second element in the column in second matrix. So this will be the final product. 10 plus 6, 15 plus 24. So the final product would be 16 plus 39. 16, 39. So finally we get a matrix of order 2 into 1. And we had already discussed before that the product will have an order of n into p, and n, where n was equal to 2 and p was equal to 1. Let me go to the working of the multiplication of a 3 into 3 matrix, which will be more challenging than which we have already discussed. So let me start with a simple example, and let me fill a matrix with random elements. But it should be a 3 into 3 matrix. That is, it should have 3 rows and 3 columns. So suppose I take it as 3, 4, 5 and 8, 1, 2 and 9, 6 and probably 3 again. Anything, any random element. It can be any random matrix. I'm just taking this as an example, so not to be confused with. And I take one more matrix, 1, 6, 4, 3, 4 and 8, 9, 7 and 2. This is it's just once again a random matrix, just for the sake of an example. And now I'll be multiplying these two matrices. This is a matrix of order 3 into 3, and this is also a matrix of order 3 into 3, as they have 3 rows and 3 columns each, and both of them are square matrices. And the product, and let's check the condition. The number of columns in matrix 1 is actually equal to the number of rows in matrix 2. So hence the condition is satisfied, and hence we can multiply them. So, and the product yielded would also be a 3 into 3 matrix, and the product yielded will also be a 3 into 3 matrix. Product to be yielded, order is equal to 3 into 3. So let's start with the multiplication. So the first element of the product will actually be a product of the first row and the first column. So 3 into 1 plus 4 into 3 plus 9 into 5. And the second element of the product will actually be a product of the first row and the second column. So 3 into 6 plus 4 into 4 plus 5 into 7. And the third row and the third element would be the product of the first row and the third column. So 3 into 4 plus 4 into 8 plus 5 into 2. And hence we'll proceed so on. So I'll try to go a bit fast with this, as I had already explained, but hence to make it more clear, I'll explain once again. So the first element in the second row of the product will be a product of the second row of the first matrix and the first column. So 8 into 1 plus 1 into 3 plus 2 into 9, and 8 into 6 for the second element, 8 into 6 plus 4 into 1 plus 7 into 2. And for the third element of the second row, it will be of the product, 8 into 4 plus 1 into 8 plus 2 into 2. and for the third row I'll go really fast as I've explained for the first two rows. The third row is similarly, but here you multiply the third row with the first column and the third row with the second column and the third row with the third column for the three elements respectively. So 9 into 1 plus 6 into 3 plus 9 into 3, that is 27. I've actually put the product over here. And 9 into 6, 54, plus 6 into 4, 24, plus 3 into 7, 21, and here 9 into 4, 36, plus 6 into 8, 48, plus 3 into 2, 6. So let us do a quick calculation and let us sum it up. 3 plus 12 plus 45 over here, 18 plus 16 plus 35, 12 plus 32 plus 4 into 5, 5 into 2, 10. So here it will be 8 plus 3 plus 18. Here it's 48 plus 4 plus 14. 32 plus 8 plus 4. 9 plus 18 plus 27. 54 plus 24 plus 21. 36 plus 48 plus 6. So let's do a quick summation. 15, 45, 60, 34, 69, 44, and here you get again 44, here you get 64, no 54, 11, 29, 52, 66, 40, 44, 27, 54, 78, so 99, 36, and here you get a 90. Yeah, so this is how you multiply a 3 into 3 matrix. Probably this is one of the most complex matrix multiplication, and you have even more complexes in 4 into 4 and 5 into 5, which you can actually use doing softwares like MATLAB, and I think it takes a lot of human time and human effort to do such calculations, and it's in fact really difficult for a normal human being to do such big calculations for a 4 into 4 and 5 into 5 matrices. After the discussion of the 3 into 3 matrix, I would like to conclude. But before conclusion, I would also like to put light on the topic scalar multiplication. Suppose I take a matrix, any matrix, like I take a 2 into 2 matrix, 3, 2, 4, 5, and I try to multiply it with a scalar quantity, suppose k. That is, the product would be 3k, 2k, 4k, 5k. The scalar quantity gets multiplied with each and every element of the matrix, and hence you get a new reformed matrix with each of the element multiplied with the scalar quantity. This similarly applies for every other matrix. It even applies for a 3 into 3 matrix and any other matrix, even if the matrix is not a square matrix. And hence I would like to conclude. By saying that it was great explaining to you all about matrix multiplication, and I would like to thank Ajit Kumar sir for giving me this opportunity to make such a video. Thank you.